today we're going to talk about equations in anesthesia. As the name suggests, the classes are quick revision anesthesia. It's going to be 30 minutes, maximum 40 minutes. Okay. I'm going to highlight the key points and I'm going to explain to you how you're going to get all these equations correct and understand it. Okay. That's the main point of the class today. Okay. Today's menu, we're going to talk about Ohm's law. What is Ohm's law? What is the application of Ohm's law in physiology? Okay, next, we're going to talk about relationship between flow, pressure, and resistance. Then how these three things are involved in equations in cardiovascular system, as in how do you going to get your cardiac output, mean arterial pressure, and systemic vascular resistance, and also how this is extrapolated and being used in other system as well, as an example, central nervous system. Then we're going to talk about how we're going to calculate oxygen content and oxygen consumption. Next, we're going to talk about oxygen delivery, or also called as oxygen flux. Finally, we're going to talk about cardiac output measurement, which is using FICK principle. I'm going to run through this. I'm going to explain step by step. If you all have any doubts, hold on to the end of the class. I'll give 5 minutes at the end of the class for me to explain. Okay, first, Ohm's law. The core recipe of the topic today is Ohm's law. Ohm's law is a law in physics, within electrical, okay, electrical law. It actually describes the flow of electrons within an electrical circuit. So for Ohm's law, you just have to remember V equal to IR. V is equal to IR. So what does Ohm's law state? It states that for a given resistance, the potential difference, okay, the potential difference is the voltage across an ideal conductor. So if we look at the graph picture here, ideal conductor is directly proportional to the current. So V equal to IR. So the potential difference for a given resistance, this is the resistance, the potential difference voltage across an ideal conductor is directly proportional to the current which flow through it. So V is the voltage, I is the current, R is the resistance. If you have rearranged it, you can get I over V over R. So how does this Ohm's law? We're not going to talk about electrical today. We're going to talk about physiology of cardiovascular system. So how does this Ohm's law extrapolated in cardiovascular system? So we're going to look at Ohm's law in CVS. As I mentioned again, please mute. Everyone else mute, please. Okay, V equal to IR, and you rearrange it, you get to I equal to V over R. So why does it so? So in this, when we talk about V equal to IR, you arrange it, you get I equal to V over R. I will be the current, electric current. V is the voltage, potential difference, and R is the resistance. So I here, the electric current. Current is something that going up and down, flow. So that is the flow that we are talking about. Potential difference of voltage is the pressure here, potential difference in pressure, and resistance to the flow. So if we just look at this equation, flow is directly proportional to the pressure, means increase in pressure will increase the flow. Whereas flow is inversely proportional to the resistance, as in when resistance increase, flow will come down. So electric current I is proportional to voltage and inversely proportional to resistance. You derive it to flow. Flow is directly proportional to pressure, but inversely proportional to resistance. So we derive it. So we look at it, flow, pressure. As the pressure goes up, flow will go up. But with the low resistance, increase in pressure, increase in flow. But as the resistance increase, the flow will come down. So in CVS, what is flow? Flow in CVS is, we are talking about cardiac output. What is the potential difference of pressure? The voltage we are talking about pressure. The pressure gradient we are talking about is the mean arterial pressure. And then the resistance we are talking about is systemic vascular resistance, either systemic vascular resistance or total peripheral resistance. So if from these equations, Ohm's law, I equal to V over R, we extrapolate to CVS, where I will be your cardiac output. Your potential difference in voltage will be the potential pressure gradient, MAP, and resistance will be your systemic vascular resistance. So we get our equation. V equal to IR, MAP equal to cardiac output times stroke volume times systemic vascular resistance, where I over VR, we want to look at the cardiac output, flow, MAP over SVR. So this is the equation for MAP. This is the equation for cardiac output. So MAP is equivalent to cardiac output times systemic vascular resistance. So if you're going to look at how we get this, V equal to IR, but we wanted this V, right? The potential pressure, this is your MAP. So R goes here. So IR, flow times resistance, cardiac output times systemic vascular resistance, you get your MAP. You rearrange it, you want to get the flow, cardiac output, that will be MAP divided by systemic vascular resistance. It's not only in CVS, in RS also this Ohm's law can be applied, but we're not going to talk about RS. I'm just going to give this example for our next class. Same, but in RS, your flow will be not the cardiac output, it's the air flow. So the gas flow, okay, the gas flow that comes in here. The pressure gradient, which is V, we use in cardiac output, in cardiovascular system, here will be pressure difference between atmospheric and alveolar, which we call it as a trans-airway pressure. Pressure atmospheric minus pressure alveolar. That's the difference. The atmospheric pressure minus intra-alveolar pressure, you get a trans-airway pressure. That is your pressure gradient. And resistance will be your airway resistance. So this is for respiratory system. So airflow is equivalent to trans-airway pressure, which is atmospheric pressure minus alveolar pressure, divided by airway resistance. So increase in airway resistance, as an example, patient with a bronchospasm and everything, your airflow is reduced. But increase in airway pressure, you will increase your flow. So if you want to ventilate a patient more with higher volume and everything, you increase your pressure, right? That's the simple example. So next, we go to cardiovascular system again. We know the simple equation that we have learned during undergraduate and everything. MAP is equivalent to diastolic blood pressure plus 1/3 pulse pressure. What is pulse pressure? Pulse pressure is merely a difference between systolic blood pressure minus diastolic blood pressure. So your MAP is equivalent to diastolic blood pressure plus 1/3 systolic minus diastolic. So this is what we have learned from beginning and everything. But we are not interested in this. We want to look into the equation that relates flow and pressure and resistance. So we are interested in this equation. MAP is equivalent to cardiac output times systemic vascular resistance. Pressure difference, flow times the resistance. So what is cardiac output? Cardiac output is stroke volume times heart rate. You have a cardiac output, you must have a volume that being ejected from your left ventricle, which is N diastolic volume minus N systolic volume, you get your stroke volume times your heart rate. So you put this into here. So your MAP is equivalent to stroke volume times heart rate times systemic vascular resistance. You increase your fluid, preload, increase your venous return, you increase your stroke volume, your BP will go up. You increase your heart rate, you give atropine, you give ephedrine, the patient is sympathetic stimulation, heart rate goes up, your MAP goes up. Your systemic vascular resistance goes up, your MAP goes up. You give your phenylephrine, vasopressors, you start your noradrenaline. All these causes vasoconstriction, increases your systemic vascular resistance and increases your MAP. So this is the full equation for MAP. So this is how we apply our day-to-day practice. When patient have a low BP, we have to find out, is it patient under volume, patient bradycardic, or patient is vasodilated, and we act accordingly. So this is just the overview of the whole thing. Again, BP is equivalent to cardiac output times SVR. Cardiac output is stroke volume times heart rate. So stroke volume depends on your preload, how much of volume you have. Then your systemic vascular resistance is your afterload. And stroke volume also depends on your contractility. How good is your heart is contracting. Okay, this is just a repetition here. So now we go back again. How does this equation is extrapolated into other system, as in central nervous system? Again, the MAP in central nervous system we are looking at is your cerebral perfusion pressure. The pressure, your flow will be your cerebral blood flow, and the resistance we are looking at as is a cerebrovascular resistance. Okay, cerebral blood flow. So you want to rearrange this to get the flow. As we always interested, how do we can increase the blood flow or reduce the blood flow in a patient with a traumatic brain injury? You do want to increase an ICP, so that's you want to reduce the cerebral blood flow. How you do it? You will maintain your CPP and cerebrovascular resistance. So we want to know how do we do it. So cerebral blood flow is equivalent to cerebral perfusion pressure divided by systemic vascular resistance. Any increase in systemic vascular resistance will reduces your cerebral blood flow. A simple example, hypercapnia. Hypercapnia causes vasodilatation, cerebral vasodilatation. So thus, your cerebral vascular resistance drop. Your cerebral vascular resistance drop, your CBF increases, your ICP increases, which is very detrimental in a patient with a brain injury. We don't want that. And to maintain a certain cerebral blood flow, if a patient will have a very huge mass increase in ICP, there is no enough cerebral blood flow, patient get ischemia, stroke out. So you have to maintain a certain cerebral perfusion pressure. That's why we always maintain achieve MAP. So MAP minus ICP is your CPP. So we always start inotrope or vasopressors to maintain a certain CPP, so the CBF is maintained. So again, central nervous system will be covered in another topic from me. So I'm just overviewing all this so you have an idea. We're going to go into more in depth about the calculation per se. So I'm just running through all this at the moment. So now the important part of it, the equations, the exact equations where you'll be expected to do calculations in exams. So please pay attention. First, we're going to talk about oxygen content. So oxygen content will be in either your arterial system, which we'll call as CaO2, concentration of arterial oxygen, okay, or content of arterial oxygen. And we're going to talk about venous. So venous oxygen content. So arterial oxygen content and venous oxygen content. So oxygen content in your blood, be it arterial or venous, exists in two forms. Either it's bound to hemoglobin, oxygen that is bound to hemoglobin. Okay, oxygen that is bound to hemoglobin, or oxygen that is dissolved in blood. Oxygen bound to hemoglobin and oxygen dissolved in blood. So if you look at this arrow, oxygen that is bound to hemoglobin. Each hemoglobin, a per gram hemoglobin, okay, 1 gram hemoglobin can bind 1.34 mil of oxygen. Okay, from the alveoli, this alveoli is rich with oxygen. When your pulmonary circulation, your hemoglobin will extract or take up oxygen into them. So how much can they take up? 1 gram of hemoglobin can take up 1.34 mil of oxygen. Remember this number. Next, dissolved oxygen. How much of oxygen can be dissolved in blood? It's very little, 0.003 mil oxygen per 100 mil of plasma per millimeter mercury of oxygen, which is the partial pressure of oxygen. When dissolved, we have to talk about the partial pressure. We'll come into this again. Remember that oxygen content, oxygen is present in two forms, either bound to HB, hemoglobin, or dissolved in blood. So again, so how do we calculate how much of oxygen is bound to hemoglobin? The formula is oxygen carrier capacity times the oxygen saturation. So we have to find out each hemoglobin have their oxygen carrier capacity and how much of the hemoglobin is saturated with oxygen. Okay, that is to find out the amount of oxygen bound to hemoglobin. And to find out the oxygen dissolved in blood, we need to know the partial pressure of oxygen in the blood times the solubility coefficient, which is I mentioned at 0.003 mil per millimeter mercury of blood. So how do we calculate this? The equation would be, to calculate the oxygen bound to hemoglobin, you need to the hemoglobin level, which we find a gram per deciliter. That's how we usually calculate or we get our results. Gram per deciliter. Remember this. This DL stands for deciliter. Times 1.34. I'll come to it. Why does these numbers exist? What is the importance of this number? Times saturation of oxygen. But in this equation, you have to remember few units and few way we put it. For hemoglobin, you have to mention it in gram per deciliter. And for oxygen saturation, you have to mention it in decimal. Means if your oxygen is 99%, you have to divide it by 100. We're not going to put it in percentage. We're going to put it in decimal. Plus, the oxygen that dissolved in blood, you have to find out the partial pressure of oxygen by doing a blood gas, either arterial or venous blood gas. You're going to get your PO2 times 0.003 mil per millimeter mercury, because 1 millimeter mercury of oxygen in the blood is able to dissolve 0.003 mil of oxygen. So what is this 1.34 stands for? It's called as a Hoffner's constant. So what is Hoffner's constant? Hoffner's constant say oxygen combining capacity of hemoglobin. So each gram of hemoglobin can combine or bind 1.34 mils of oxygen. So if you put it at oxygen content, arterial oxygen content is 1.34 times the hemoglobin concentration times your SaO2. okay, plus 0.003 times PaO2. Just for venous is the same. Just in terms of SaO2, we're going to take a SvO2. We're going to take a venous blood gas. We're going to take a SvO2, oxygen saturation in the venous blood, and the partial pressure of oxygen in the venous blood. Just take it as 0.003. You don't have to put the 1 at the back. No need to be very rigid about all these things. Okay, we'll go into this. I'll tell why is it not so important shortly. So remember this equation, oxygen bound to hemoglobin, you're going to times with hemoglobin concentration times that Afner's constant, which is the oxygen combining capacity of the hemoglobin, times the saturation of the oxygen in decimal point, plus bound to blood will be millimeter mercury of partial pressure of oxygen times the 0.003 mil, which is the solubility constant. So this is the commonly mentioned equations in most of the book. But some books or some online website or some notes may use some other few numbers just for your information, so you don't get confused. I'm going to talk about that as well. So what are the variation? This is the most commonly used equation, the numbers. The numbers that usually vary is this Afner's constant and the solubility coefficient. So first we talk about Afner's constant. Most of the books mention 1.34, but in some books you may see this 1.39. So why this is 1.39? The theoretical maximum oxygen carrying capacity of a hemoglobin is 1.39 mil. I mean, the hemoglobin is a perfect hemoglobin, in which for adult is HbA1. If all our blood, the whole blood is only containing HbA1, then we can take this as 1.39. But in reality, our blood has 97% is HbA, but another 3% we have all the other hemoglobin, which has less oxygen carrying capacity, HbA2, HbF, HbA1c, carboxyhemoglobin, methemoglobin, sulfhemoglobin. So this hemoglobin does not have the perfect oxygen carrying capacity. Thus, we have to give a correction factor. So we use 1.34 mil. This is the reality number. This is the ideal. 1.39 will be ideal, which is not practical. So we use 1.34. Hope everyone understand. So in exam purpose, please use 1.34. Next, this solubility coefficient. Solubility coefficient follows Henry's law. We're not going to go into Henry's law. That will be in a physics class. I will talk about all the gas laws. So what does the Henry's law say? 0.03 mil of oxygen can be dissolved in blood per millimeter of mercury. Okay. So it must be mentioned in deciliter of blood. Since we hemoglobin, we're putting as deciliter, we also deciliter. So what is deciliter? Deciliter means 1 deciliter is 100 mil. So that's why we use deciliter. Okay. So 0.03 mils per millimeter mercury of oxygen per 100 mil of blood. So in 100 mil of blood, which has a certain millimeter mercury of partial pressure oxygen, 0.03 mils can be combined. So this value is the one that mostly mentioned in many books. But there is some books use kilopascal instead of millimeter mercury for partial pressure of oxygen. So you may find this number 0.225 or 0.0225 will be bundarkan jadi 0.023, because when they use kilopascal, 1 kilopascal is equal to 7.5 millimeter mercury. So 7 times 0.003, you will get 0.0225 and then 0.023. So some book may mention this. So you have to pay attention to this kilopascal. So if they use kilopascal, they're going to use 0.023. If they're going to use millimeter mercury, they're going to use 0.003 mil. Okay. So, but do we have to go through this much of a headache for this dissolved solubility constant? No, it's not, because it's a very insignificant amount that contributes. Why is it so? I'll explain to you now. This is your ODC curve. So if you look at your ODC curve, we will talk about ODC curve. I just want to show a few points. We have a point where, arterial point where in the alveolar, when your PaO2 is 100 millimeter mercury, your saturation is almost 98%. It hardly reaches 100%. It's usually 98%. This is your arterial blood gas. When you take arterial blood gas in a normal person, usually you'll get a PaO2 of 100 millimeter mercury. At 100 millimeter mercury, according to ODC curve, you will get 98% of oxygen saturation. And you take a venous blood gas, the PaO2 will be 40 millimeter mercury. And during the 40 millimeter mercury, your SpO2, the SvO2 will be usually 75%. So let's calculate. Everyone can calculate on your own while I'm going through as well. So let's take a patient has a 15 gram per deciliter of oxygen. The SpO2 is 98% as per the ODC curve, and PaO2 is 100 millimeter mercury. You take an ABG. In the ABG, you get a SaO2 of 98%. You don't have to look at the pulse oximetry SpO2. You take ABG. In the ABG also, there'll be SaO2 mentioned. So you take that SaO2. So let's say it's mentioned 98%, and your PaO2 is 100 millimeter mercury, and HB is 15 gram per deciliter. This is in a healthy individual. So we calculate the CaO2. So how are we going to calculate? This is the equation. We talked about it. So let's calculate. I have given you the equation. I have given you the values. So first we calculate the HB bound oxygen. So HB bound oxygen is saturation. So saturation is 98. We have to put in decimal, divide by 100, times the hemoglobin concentration, 15 gram per deciliter, times the Affner's constant, 1.34. So 0.98 times 15 times 1.34 comes out 19.698, where 19.7 mil oxygen. This is your arterial oxygen content in a patient who are healthy individual at SpO2 of 98% and a PaO2 of 100 millimeter mercury. So how much is the dissolved oxygen? So dissolved oxygen is 0.003 times the PaO2. The PaO2 is 100 millimeter mercury. So 0.003 times 100, you get 0.3 mil oxygen. So you calculate total will be 19.7 plus 0.3, which is 20 mil. So this 0.3 mil, how much it contribute to the total oxygen content? 0.3 divided by 20, 1.5% only. It's hardly very important. So it's very insignificant. So if you wish to omit to calculate this oxygen bound in blood, it's okay. Okay, it won't make much of a difference in your answer. But for equation, say you must know this is the full equation. So let's calculate for venous blood now. So we'll calculate the CaO2. But when I have said that dissolved oxygen contribute very little, 1.5%. But when does it become very important? In a hyperbaric chamber. When patient in a hyperbaric chamber, we're going to increase your PaO2 to very high. It's going to go up to 660 to 760, sometime at 1 bar. Okay, 1 atmospheric pressure. So that when this goes up, when you're going to put it here, this goes up, of course, this will become significant. So you're going to read up on that hyperbaric chamber. How in hyperbaric chamber, the dissolved oxygen concentration going to go very high. So next, do for venous blood gas. You take a venous blood gas from your CVL or anything. HB is still the same, 15, but SVO2 is 75%. Your PVO2 is 40 millimeter mercury. We're going to do the same calculation, 75 over 100 for your saturation, times 15 times 1.34. You get around 15.1 mil. You just bundarkan here. Then dissolved oxygen is going to be even lesser because your PaO2 is only 40 millimeter mercury, 0.12. Calculate total venous oxygen content will be 15.22. The contribution of the dissolved is just 0.7%. Again, but in hyperbaric chamber, this can be significant. In a normal patient, we are breathing at normal room air or in normal oxygen, it's not going to make much difference. But in a patient with hyperbaric chamber, your PaO2 or PVO2 going to go up very significantly. Then this will become a significant number. So now we know your CaO2 is 20 mil and your CVO2 is 15 mils roughly. Okay, so we have calculated arterial and venous oxygen content. So next we move on to next equation, oxygen consumption. So this is another equation that you must know. So what is oxygen consumption? Oxygen consumption is the standard oxygen consumption value equivalent to 1 metabolic equivalent. This is what you do your METs. Okay, when you do your pre-op assessment, when you talk about METs, this is what we say METs. METs is resting oxygen consumption of a 40-year-old 70 kg male, which is 3.5 mil per minute per kilogram. That is your oxygen consumption. So in a 70 kg male, you have 3.5 mil per kg per minute. Okay, it means at rest, at one patient, if you have a MET, the MET is equivalent to 3.5 mil. So usually we want the patient to have 4 METs. 4 METs, I mean 4 times 3.5, you're going to get around 14 mil per kg per minute. So in a 70 kg adult, what is the total oxygen consumption of the body? So 70 times 3.5, you get 245 mil oxygen per minute. So at the rest, a 40-year-old 70 kg male will use around 245 mils of oxygen per minute. The value from each book can range from 240 to 260 mil per minute. You can take in the middle 250 mil per minute. So how are you going to calculate it? This, they already given you the value, so you can easily calculate. But how are you going to calculate it using an equation? So is it this value that given is real? Is it exactly how much they use? Let's calculate. So oxygen consumed is oxygen delivered minus the oxygen returned. From the alveolar, the oxygen goes into your systemic circulation and returned to you by your venous return. So how much oxygen went into the arterial system and how much came back via the venous system? The difference between these will be your oxygen that has been consumed. So oxygen, the arterial flow minus the oxygen in venous flow. So flow is cardiac output. So the flow times arteriovenous difference of oxygen. We have calculated arterial oxygen content and we have calculated venous oxygen content. So we have to find out the flow. If flow times this, the arteriovenous oxygen content difference, we will get our oxygen that being consumed. So what is flow? What makes our oxygen go? It is the cardiac output. Cardiac output is the flow of blood in arterial and venous as well. Okay, that is the cardiac output. So cardiac output times your arteriovenous oxygen difference will be your oxygen that being consumed. So your VO2 equation is equivalent to cardiac output times CaO2 minus CvO2. The cardiac output also must use deciliter per minute because in our oxygen content equation, we use deciliter for hemoglobin. So we have to standardize all these. I will come to explain how do we do this as well. How do we going to convert our cardiac output into deciliter? Okay. So this is the equation for the oxygen consumption. So let's calculate again. How much is whether this value that has been given here, is it true or not? By equation. So let's do it again. So if you say we have already calculated just now your cardiac CaO2 minus CvO2. We have calculated already just now. The CaO2 is around 20 mils oxygen and your CvO2 is around 15.22. And your cardiac output, so your arteriovenous difference, we already get difference is 20 minus 15 lah. We take roughly 15.22, we just take 15 lah. So the difference in arterial and venous is 5 mil oxygen. And your cardiac output, we know in a roughly a 40 kg man will be, if you have a stroke volume of 70 and heart rate of 70, 70 times 70, 4.9 liter, which is around 5 liter, 5,000 ml, which is 5 liter. So cardiac output in an LT male will be 5 liter per minute. 5 liter per minute, which is equivalent to 5,000 ml per minute. And I've told you 1 deciliter is 100 mil. Okay, so 5,000 divided by 100 mil, you get 50 deciliter per minute. So cardiac output 5 liter is equivalent to 50 deciliter per minute. So now we put this into our equation. So VO2 is 50 times the difference of arteriovenous oxygen difference times 5, 250. The same as how we calculated, almost there, 245 to 250. See? So this makes sense. So if you have another patient, you want to know how much of the oxygen being consumed in a patient also, you can do this. You take an arterial blood gas, you get a venous blood gas. If you have advanced hemodynamic monitoring, it's going to show you your cardiac output. So you can do your own calculation. Okay. Next equation will be oxygen delivery, DO2, or in some books mentioned as oxygen flux. So what is oxygen delivery? So we talk about venous oxygen, where oxygen consumption is oxygen in arterial flow. Okay, the delivery is oxygen in the arterial flow. This is the return. So your DO2, what we are talking about now is only the delivery. So delivery means we are only concentrating on arterial oxygen content. So simply flow times arterial oxygen content is your oxygen delivery. So oxygen delivery is equivalent to cardiac output times CaO2. We have done this already just now. This is the full equation. You know your cardiac output 50 deciliter, 5,000 divided 100, you get deciliter. And this is your full equation of your CaO2. We have discussed it just now. And we already know CaO2 just now, we got a value of 20 mil. So 50 times 20, you get around 1,000 mil of oxygen. So for each cardiac output, 1,000 mil of oxygen is being sent to systemic circulation in the arterial flow. Okay. This is just a repetition. We have done this equation just now. CaO2, how to calculate arterial oxygen content has been done. And we already know cardiac output, how to get it in deciliter. 5,000 divided by 100 because 1 deciliter is 100 mil per minute. So 50 times 20, you get your 1,000 mil oxygen. So now you already know your arterial oxygen content. You know your venous oxygen content. From that, you know how to calculate your oxygen consumption, and now you already know your oxygen delivery as well. So all these we can find out cardiac output measurement. So now we go retrospectively. Previously, we do all this equation. Now how we can do a cardiac output measurement? Cardiac output measurement is done by a law called Fick's law. So Fick's law said uptake or excretion of a substance by an organ must be equal to difference between amount of substance entering and amount of substance leaving. So simply say amount of substance entering is your arterial oxygen content and your amount leaving is your venous oxygen content. Okay, instead of using any substance, we're going to use oxygen to calculate the cardiac output. It's the same. If you look at this venous oxygen consumption equation, venous oxygen, oxygen consumption, not venous, sorry, typo. Oxygen consumption equal to cardiac output times arteriovenous oxygen difference. You rearrange it. For cardiac output will be venous oxygen consumption divided by the arteriovenous oxygen difference. So I'm just going to go ahead and show that equation now. So rate of uptake or excretion is your consumed. The difference is like, as I mentioned, arterial oxygen delivery, venous oxygen return. There's a difference will be your oxygen that being consumed, the oxygen consumption. So you rearrange it. So oxygen consumption is equivalent to flow times your arteriovenous difference. You rearrange it to find out the flow. The flow will be oxygen consumption divided by the arteriovenous difference. So to find out this, we have to find all this. We have find out the oxygen consumption. We have find out the oxygen delivery and oxygen content. We have done all these things. So we can easily do this. So how are we going to do this? Once you have your cardiac output, you have your oxygen consumption. So oxygen consumption just now was 250, right? And 250 and your arteriovenous difference, as I mentioned here, we go back here. Your oxygen consumption by this calculation, 70 times 3.5 mil, 70 kilo times 3, you know you're around 245 mil. And you know your arteriovenous difference is 5 mil. So 245 or 250 divided by 5, you will get 50 deciliter. You're going to rearrange. 50 deciliter is equivalent to 5,000 mil, equivalent to 5 liter per minute. So just to put all these in one, we have talked about oxygen consumption equation. We already talked about oxygen delivery equation. We already talked about this and we already talked about this. So we're going to put all these in one, which is a summary for today. The oxygen is being delivered in arterial circulation is 1000 mil. How do we get it? We get it by this equation. Cardiac output times your CaO2. 50 times 20 is 1000. Okay, this 1000 goes into this your circulation. This is the oxygen. Okay, this is oxygen. And the flow of blood is 200 ml that is going and is being consumed. So the arterial oxygen content in this blood will be, you already know, CaO2, which is around 20 mils. Okay, and then around 50 mil per liter of oxygen being consumed. 50 mil per liter oxygen being consumed. So we have 5 liter. 5 times 50 will be your 250 mil of oxygen being consumed. So then the venous return in oxygen, which has this CbO2, then your cardiac output, we will get back return. So 1000 minus, when you calculate this, your venous oxygen content was 15 mil just now, and you knew your cardiac output 50 deciliter. 50 times 15 is 750. 1000 minus 750, you again get your 250 mil of oxygen. So you are just reassuring. If you're going to use the 70 kilo times 3.5 mil, you get 250 mil. You do the exact equation just now also, you get around 250 mil. You're going to calculate the oxygen delivered minus the oxygen returned. The difference between these also 250 mil per unit. So these are the summary of all this equation in one. So the VO2 is equivalent to cardiac output times your arteriovenous difference. So which is equivalent to 250 mil. Which is, then you want to calculate your cardiac output, you just rearrange this equation. Your cardiac output is equivalent to oxygen consumption divided by arteriovenous difference. Your oxygen consumption is 250. You know your arteriovenous difference is 5, which comes to 50 deciliter, come up to 5,000 mil, which is 5 liter. So that's all for this. I know it's a bit of rush, but this is a quick revision class. So I will share the recording later. You all can have a look at it also. Before we finish, it's already almost 35 minutes. I have a 5 minutes for question and answer. I'll wait until 10:10. If there is no question, we'll end this session today.
Dr. Vimal.
Yep.
So the oxygen consumption is normal is 3.5 mil per kg, which is equivalent to 1 meds.
Okay.
So 3.5 times 70 about 250 lah.
Yep.
But then the usually we say the normal meds is usually the normal is 4 meds and above. So the normal value. So why the normal value is 250 only?
Meds is metabolic equivalent of task by activity status index. Okay. So it means how healthy you are is meant by how good are you to increase your oxygen consumption and still stay healthy, still stay without being exhausted. If a person can increase the meds by four times from 3.5 mil, 4 times 3.5 mil is 14 mil, right? 14 mil. If a person can increase the meds by 4 times for doing that activity without getting exhausted, without getting collapsed, it means his heart is good. His heart is cardiovascular system is capable of increasing his oxygen consumption to meet its demand. Whereas if a person say meds less than 4 mean, they cannot even increases their oxygen demand by themselves without getting exhausted. Their effort tolerance or their endurance is very low. As an example, if a person is meds more than 7 or 10, it means they are athletic. They can increases their oxygen consumption to certain level until that level without being exhausted or without being collapsed. That good they are. Their cardiovascular system or cardiopulmonary system is very good until they can increases their meds. They can increases their oxygen consumption to meet the demand without getting collapsed. Compared to someone who can't, let's say we say someone is meds less than 4, it means their cardiopulmonary system is not good enough. They don't have that much of reserve to increase the oxygen consumption to meet the demand. It means they are not good. They are physically not fit. A physically fit person can increase the oxygen consumption by aerobically without going into oxygen depth or anaerobic respiration. That is the meds equivalent.
So theoretically, if we take an athletic person and calculated the resting oxygen consumption,
it will be high.
Will be higher than 3.5.
Yeah, their resting oxygen consumption, resting plus exercise. That's why you do exercise. During your exercise, your oxygen consumption goes very high, right? It will increase for sure. Your oxygen demand is high, whether you are able to supply the demand or not. That is why the meds calculate. We ask if a person is able to do a marathon, it means his cardiopulmonary system is good. It can increases its oxygen consumption to a certain level to meet before he's going into anaerobic respiration. If a person is not fit but is pushing, is going to go into a anaerobic respiration and he's going into oxygen depth. That's why they faint or collapse or they have a heart attack. They go into ischemia. Okay?
Okay.
Any other question? One more minute to go. No question. We're going to end the session shortly.